Welcome to the next video in abstract linear algebra. This is video 6 on basic uniqueness properties for vector spaces. It corresponds to chapter 1, section B of the textbook. So to begin with, we're going to discuss the uniqueness of the vector 0 in any given vector space over a field F. So effectively, we're going to show that the only additive identity is the 0 vector. Put more thoroughly, what we're going to show is this statement right here. If you take any vector in the entire vector space and it has the property of the identity, that is to say, when you add it to any vector, then you get, right, the vector is unchanged, right? You just get that vector back again. If that is true for this vector v, if it has this property, then v must be equal to the 0 vector, right? So basically just showing that this one vector, the 0 vector, is the only vector in the space which has this property. So, of course, the way to begin such a proof is to let v be such a vector and then start reasoning about it. So now that we have this vector v, we want to show that v equals 0. How are we going to do that? Well, let's use all the properties of objects that we have around, and I think it makes sense to, maybe kind of like get v and 0 together in the same equation, right? That's probably a good productive idea. So let's write this. We're adding them together. We know we can because they're both vectors in the vector space, and because it's addition and for all the properties that we've assumed, if you look at this property of v, we know that this must equal the 0 vector because of this property that we assume v has. But also, 0 has essentially the same property. So we also know that if you take 0 plus v, you just get v, right? Using the sort of identity property of 0 this time. So you get that right there. Well, actually, this is what we wanted to show this whole time, and so the proof is already complete. Okay, in the next theorem, we're going to do a very similar proof, but this time for the uniqueness of inverses. So again, here the idea is, if you pick any x in our vector space, and then you pick some other vector, I'm now going to call that v, also in the vector space. If v has the property that defines the inverse of x, right? This is the property that defines the inverse of x. So if v has this property, we are going to show that then v must actually just be the inverse, the additive inverse of x, right? That unique, we don't assume that it's unique, that's what we're proving right now, but that element of the vector space, which the axioms or the definition of a vector space tells us must exist, right? This one we know exists due to the properties of a vector space. And so if anything else has that same property, it must just be equal to the one that is guaranteed by the properties. Showing that there is only one of them is basically the point. So of course we just initially barely even think about it just as a matter of proof strategy. We're just going to let these things exist. Now, what are we going to do with them? Again, it seems like a good idea to try to get v and, in this case, x, right, the additive inverse of x together in the same equation. So maybe if I start from knowledge of this equation, I could add the inverse to both sides, right? So, because if they are equal to each other, then we must have that x plus v plus negative x is equal to 0 plus negative x. And of course, we can, having done this, we can cancel on each side so that the left-hand side turns, right, the x and the minus x, those combine to become 0. And then we take 0 plus v, so the left-hand side simplifies to v. Of course, I am using implicitly associativity and commutativity and a number of properties without sort of fully being explicit about how I'm using them. If anyone wants a more explicit proof than this, let me know. But I think, it's probably contained in the textbook. So I mostly, in communicating this, want to give a convincing proof and also indicate how to think about approaching proofs, right? Like maybe sort of fill in the aspects of proving theorems that are not communicated by the textbook. The textbook has sort of thorough and complete proofs. I want to maybe present more of the sort of psychological part of like, how do you think about these things and how do you approach these proofs? So anyway, but if you want a more thorough proof in the comments, maybe let me know. And if I have time, I can try to record a more thorough explanation. But for now, I'm going to just take it for granted that we're okay with using associativity and commutativity without too much explanation. So the left-hand side turns into v. The right-hand side, because it's 0 plus the inverse of x, turns into minus x. And this is exactly what we wanted to prove, so the proof is complete. If you appreciated this content, please like and subscribe. And if there's anything that we discussed here where you'd like to see it elaborated further, I might be able to answer questions in the comments, or for substantial topics, I might make an entire video and add it to the playlist.